So why don't we start? It's been a while since I gave my last lecture. I just heard from TA. You guys did very well in the second exam, and I hope you continue. And the final exam, as we said in the beginning, the final exam will cover the last 1/3 of lecture, as well as general questions covering entire class. So just make sure you don't forget. So, so that exam has a little bit higher weight than previous two. And then just take that into consideration. So we're going to ask you some general questions across entire class. Now, I noticed you may remember the prediction I gave when I gave my first lecture. The number of students in the classroom will decrease as the temperature outside increase. And it seemed to fit my prediction. But anyway, but let me, since I'm a course director, I have to say this to you and to your friends who are not here. And what I said is at the very beginning, that we, as an instructor and TAs, are here to help you. That if you come to every lecture and do very well, we're extremely happy. If you don't come to lecture, not you, but your friends in the class, if you don't come to lecture, you are doing fine. We're just as happy. But if you don't come to lectures that don't do well, that's trouble. And you have 1/3 of a semester left to catch up. Be sure to tell your friends, roommates who you know might be struggling to catch the trend. And there's still 1/3 of semester left. Okay. So what I will do today is to discuss somatosensory system. And then I have 2 more lectures to give on Friday and the next Monday. I'll go back to talk about some aspect of auditory system that I did not get a chance to talk in my previous lectures, as well as neuron prosthesis device that is a cochlear implant and other things in auditory system that you might find it interesting. So somatosensory system is one of the 3 major sensory systems we discuss in this class. You have heard auditory system from my lectures, and the visual system from Dr. Connor. And in fact, you have heard actually another system, vestibular system from Dr. Cooling. Now we'll talk about somatosensory system. This is a system actually concerning our everyday life most, probably among everything. Let me see if we can tell. Okay, so that's better. So this is something that is very intuitive, that you don't need an instrument, a device, a computer to show what's going on. So somatosensory system is a general term for a lot of sensations we feel through our skin. And one of them is most common one is called as a touch. Okay. So what is touch for? Touch is everything. Touch is everything in our life. That we feel each other, and there's a mother and a child, or you and your friends, and we use that to feel the object in sports, and of course instrumentation that we feel if you play instrument, and that you know what does it mean for certain system. Now for individuals who lose, let me turn this off. Oops, oh, I don't want to do this. Okay, so for individuals who cannot read because he or she is blind, somatosensory allow people to read the form like this that you might see now in the ATM machine, other places. Now, of course, you use this to feel the size of an object. If you're a sculptor, and that's how you feel what you are making, okay? And vibration is extremely important sense of our hand. So for example, there's always demonstration I give it to you to show people how important, how sensitive our fingers are if you don't remember this. So for example, underneath of this table, there's particle surface. Okay, you don't see it, I don't see it. But I stick my finger here, I can feel if there are grooves there, nail there, so far so on. In fact, I don't even need my finger. If I take something rigid, I just lightly touch here, I got everything. My mind can reconstruct the 3D picture of a surface that I don't feel, I don't see. Okay, that's all come from vibration that our sense feel. So in this lecture, we'll discuss what are beneath the fingertip that allow us to feel all of this, from a very intimate touch to vibration to other things. Okay, that's what we need to understand. Now, the somatosensory system are part of the nervous system that are connected from, for example, a skin surface. That we use a finger as an example. And of course, the entire skin surface are connected. And the neurons from there, a signal from there, from the receptors, we'll talk about in a few minutes, what they are. The touch or vibration are converted into action potentials, travel through axons, through dorsal root ganglion cells, spinal cord, and that is showing here, all the way to the brain. Okay, this is the central nervous system we talk about. Now, there are two types of fibers here. I plot here. One of them is for mechanosensory efferent fibers. Another one is for pain and temperature. We'll dive into them in a few minutes. So somatosensory system covers everything. But I want to contrast this to auditory system and the visual system you have heard. So when we discussed auditory system earlier in my lecture, do you remember the equivalent of course, the fingertip is our inner ear. Okay. How many type of receptors are in the inner ear that are responsible for our hearing? How many type? How many? Can people name how many type? How many type of receptors? Yeah, which hair cell? Yes, it's one, but there's a name. Anyone name? There's more than one type of hair cells, right? Do you guys remember which two type of hair cell we talk about? Inner and outer. Yeah, so which one is responsible for hearing?
Mostly the outer.
Inner or outer? I should put this on the exam now, no. You got it right. I mean, it's inner hair cell. So in our ear, so I'm bringing you back for your benefits to since you need to go through review anyway. And it's also for you to contrast, to see what's the system like. Because as I said earlier, one easy way for you to learn and appreciate a different system is to compare them at every level. So now we're comparing at the sensory level, so the receptor level. In auditory system, there are two types of hair cells. The one that is responsible for hearing, that is equivalent to this kind of receptors that send a signal into the brain, is called inner hair cells. There's only one kind of inner hair cells. Inner hair cell, that's it. There's no A, B, C, D, E, F, G, just inner hair cell. Okay. If you destroy inner hair cell, you don't hear anything. Then there's another type of hair cell called outer hair cells. Outer hair cells serve to function for the efferent from brain to outside. Do you have a question? Okay, so if you lose outer hair cell, you lose some sensitivity, but you don't lose hearing. Okay, so there are differences between inner and outer hair cell. These are very fundamental that by now you may want to keep that in mind. But in contrast, in a visual system, now let's move to visual system. You heard not too long ago, the equivalent of a device here is retina. So how many cells in it? How many receptors? How many type of receptors in retina? Which two?
Rods and cones.
Right, rods, cone, correct. Okay, there are two, and you remember Dr. Connor discussed their different functions. Now in the somatosensory system, what you learn here, there are many. There are too many to list for now, and we will see a chart. So this will show you the design of the nervous system. By the time I get to somatosensory system, we have a lot. In general, there are three general categories. There are receptors for what we feel, we call it touch. Then there are receptors for what we feel, a pain and a temperature. At least three major categories. They're all called somatosensory system, all underneath our fingertip. Okay, so if I take a needle, puncture tip, I feel touch, I feel the pain. If a needle is just get a burn on the fire and punk here, I feel the temperature. So it all comes through the fingertip. Okay, and then for the touch, for somatosensory, for the mechanosensory, then there are more subtleties, and then we'll go dive into. Okay, so now this is the reason we talk about the somatosensory system at the last, because at the receptor level, this is the most complicated among all sensory systems. Okay, now the action potential goes into dorsal root ganglion cells, the spinal cord, then go into brain, and it depends which part of the skin. Our spinal cord are divided by different parts. For example, here, okay, as you can see by color, your upper limb, necks, back of the head, all goes into here, cervical, and then your middle of the body here, lower body here. That's why when based on this, you know if a person has an injury here, by accident, hit by a car, fallen off a bike, then the lower body cannot feel. So the higher injury is, the more dangerous. If you just have an injury here, you might lose here, but it's still here. But if you got an injury somewhere here, in the back here, it's really dangerous. Your entire body is more or less paralyzed. Okay. This is how the things are laid out. Okay, and there are all the terminologies that go with that. Okay, now in terms of modalities, I said three. Actually, there are four. The fourth modality is itch. Okay, these are four modalities within the somatosensory system: touch, pain, temperature, itch. Okay, itch is very new. We don't talk about this in textbook. In fact, in the recent years, there has been very interesting study on this. For example, why we need to itch? If you don't feel temperature, you get a burn. If you don't feel pain, you get injured. You cannot survive. This is actually very interesting. I don't think we scientists settled it, but keep in mind, maybe one day you will do research on this. Why we need to itch? Itch, you can imagine in our life, if we don't have a sensation, we probably live on, right? There are some theories saying that itch is a mechanism for us to defend, for example, such things as get bites by insects. Insects bite you, there's a chemical here, there's itch, you feel it. Otherwise you don't feel, they get infected, so on. But there are all things going on here, okay? This is what we know every day. For touch, we use this for feel spatial form, feel texture. And I told you spatial form, use that example of the feeling the table surface. Texture, I feel, you close your eye, you feel this is skin, there's a clothes, this is my pants, different texture, all of this from here. For movement, for flutter, for vibration. Okay, all of that. And each of them is associated with specific receptors that we're going to go through quickly. And then for pain, we have different pain. We have pains that is burning and the pricking pain. And then, of course, for temperature, we have a warm and cold. Now, each of these submodalities is associated, one with the receptor, two with specific fiber. Okay, and that we see here, we're going to show you more data. Particular receptor and particular fiber together support one submodality. Okay, now let's look at this tactile receptor. Tactile receptor means touch. Okay, so here's the anatomy of what's beneath your fingertip. We use the primate or human fingertip as an example because we have most developed fingertip. If you pick up fingertip of a mouse, for example, they don't have that many receptors. So here we use human and non-human primates as a model system for discussion. So here's the finger surface. Okay, you have a nerve ending here. Then you have several, we call, for example, this is called Messner capsules here, green, and Merkel cell here, and even deeper we'll have Ruffini endings, and even deeper we'll have Pacinian capsule. Here is a very small distance, it's like a millimeter or two. So we have, the key here is for each of these receptors, they serve a different role in supporting the sensation that we mentioned earlier. Okay, there are superficial ones here, there are deeper ones here. Okay, now what do they do? For example, here, let's look at the ones near surface. Messner's capsule or Merkel cells here. There's a skin surface. Now, you should be familiar with the notion of receptor field now, because each of the neural cells is connected to the axon. Therefore, when skin feels touch, there will fire action potential. Therefore, you can derive receptor field. Okay, reciprocal field of these superficial shallow layers receptors tend to be small until here, and for the deeper ones tend to be large, because if you take a very fine needle, lightly touch the surface here, you can only activate the shallow ones. You have to apply certain force to indent the skin to activate the deeper ones. So this is one way to separate them, size of reciprocal field. And as we discussed in one of my earlier lectures, the smaller reciprocal field, the finer resolution you will have for your skin or for your visual system as well. Another way to differentiate them, this is unique for somatosensory system, is to see how these receptors adapt to change in time. For example, if you touch it and stay there, that's one kind of touch. Another touch and go, right? So this type, for example, Messner's copper sole, we call it rapid adapting. That is, if you apply indentation, not touch, stay touch. It's a touch and stay there. You can see it gives action potentials at the beginning when touch takes place. And then adapted, nothing happened. This is action potential. And this type is slowly adapting. If when you touch here, stay in contact, they continue firing. Okay. This, why we have this? In a few minutes, we'll show you an example. The size of reciprocal field determines the resolution, how small things can feel. And these properties determine how you can tell different textures, I will say in a few minutes. And that's why the nervous system come up with this. Similarly, for this two type of receptors, you have rapid adapting and slow adapting. Okay. Now, here's a table showing you all the details about mechanical receptors. Okay. And I don't expect you to memorize this, so don't worry about it. But let's go through it. At least you know where to look for, if you need to study this further. So if you look at the receptors that have a small reciprocal field, that's this two type of Merkel and Messner that are near surface. Okay, and you can see the axon diameters where they are. And the conduction velocity. Now, does anyone still remember the conduction velocity you measure in the frog nerve lab we did it together? All right, so that conduction velocity you measure should be roughly in this range, right? Remember, you measure it. I think somewhere you measure between 30, 50, 60 meters per second. That's actually, this is a real conduction velocity here. And then this line shows you what kind of function this is for. For example, for Merkel cells, for form and texture, and this is for motion detection, so far so on. And then there are a lot of numbers here, okay? And whether it's a slow adapting, rapid adapting, and frequency range. Now, frequency range is a line, actually, is very interesting. Okay, this is very interesting. There's at least one thing you can remember from this form. That is, when you, for example, these days, if you drive the car, I believe most of you drive the car, basically you have a driving license. When you drive a car on a highway, quite often you run into a situation where you somehow maybe not pay attention, about to fall into sleep. Your car steers towards the side of the road. Then you feel vibration. Do you guys feel this? Okay, that's because engineers now, in last probably 10 some years, not 20 years, has put grooves on the roadside. Okay, so that actually, when people design that, they take into consideration of these parameters. So now I'm just linking you, so why these are useful even for their. So they want to design in such a way that when your car runs, that vibration generated that you feel from the steering wheel would be optimally near the peak of your feeling, so that it becomes most sensitive. If they make that so fine, you run here, you're gonna feel it, because now you feel it, we're never gonna vibrate, right? You have feel it. So if you design that properly, I actually don't know exactly what is parameter. You can go to measure. I assume if our engineer knowing this, I will design that so that some of our receptors' sensitivity is matched. Therefore, drivers with speed they take into consideration would be most sensitively to this. Okay. Now, there are larger receptors. We talk about pacinium and ruffini that has different properties, and you can look here. So I'll let you to study this. But you should actually go through here. At least you know the difference between the two. Now, but how does a nerve sensory system knows vibration, which I talk about? First of all, let's take one kind of this called pacinium. This is actually most interesting. So where they are? Let me just remind you. This is one that is deep in the skin. Okay, pacinium corpuscle. This is one actually exactly the one that is responsible for field vibration. So if you play a violin, your finger feels a string vibration. That's because of this, because of pacinium. Okay, so pacinium is the one that feel, and you can see the maximum peak sensitivity is 200 hertz, much higher than the rhythm. The rhythm feels a very low vibration. The high frequency vibration it comes from pacinium. So the way it works is the following, that explaining here. When the skin has a deformation here, it opens the channels that potassium and other things are coming, and that generates action potential around here. Now, this is the mechanism that you have learned multiple times now in this course and as before. The difference between this and the other cells in the body, like hair cell and the retina cells, because this channel is sensitive to the pressure. Now, do you guys still remember when we discussed the inner hair cells, what make inner hair cell depolarized? Do you remember what caused inner hair cell depolarize, therefore action potential generate? What is the beginning? Well, there's, do you remember the example I gave it to you? If there's inner hair cell, this hippocampal memory, their hair cell bundle, there's a mechanical channel here, like a spring. When they push one way, pull it open, iron flow. Okay. Now here, it's actually the pressure that forces that channel open, and the rest you all know. Okay, so if you were to measure, going back to our vibration, if you were going to measure the sensitivity of your skin to vibration, and then you make some kind of like a tuning. If you take the vibration frequency, it tests a different frequency and measure threshold. The lowest threshold is here, about 200 hertz. Now, given what I have just discussed, if I ask you which receptor is likely responsible for this, which one? Pacinium, the one we just talked about. Now, these are contributed by all other receptors, but this one, the one that is about 200 hertz, the most sensitive, is called pacinium. Corpuscle, we talk about it. Now, those are receptors, and the receptors are connected to efferent fibers. Okay, in optic nerve, I'll go back. I'm just keeping going back to force you to link them so that you remember better. So we talk about hair cell. What are the efferent fibers that connect to hair cell, inner hair cell? How many types? How many times did we discuss? We say there's an inner hair cell that is responsible for hearing for efferent. And the inner hair cell connected by optic nerve, right? That's fiber. How many types of optic nerve did we talk about? We won't talk about one. Okay, I never differentiated different subtype. The fact is that if you read in fine detail for research, there are two types. But in this class, we won't talk about one. In textbook, most of them don't touch. So there we just say it's optic nerve. But here is different. Here, in somatosensory system, every receptor has its own fiber. That's what we'll talk about fiber here. So what you see here is the following. For example, in this sketch showing you superficial receptors, mercure and messenger, that are connected by certain fibers, and they are by other fibers. Okay, fibers are different. And the fiber, and also the ones for cold and each are different. So here I show you the fiber size now. Why fiber size matters? One moment, I'll give you one example you probably remember for a long time. So if you look at the fibers that connect to receptors for this kind of sensations, right? We saw the touch, proper reception is a part of this touch, pain, temperature, itch. So for the touch, the ones we have discussed so far mostly, they're connected by these kind of fibers. Okay, this is a notation fiber. This is a C fiber, the thin, and then the alpha, beta. These are thicker fibers. So they're action diameters. Now, for what we have learned, you have already learned the larger diameter fiber, the fast action potential. So remember, for the frog nerve experiment, we did it together. I explained it, and some of you might follow up with reading. If you take frog nerve out, it has many fibers. Some are thicker, some are thinner. Right? Thicker fibers are actually going to travel faster than thinner. So that's why sometimes some of you might observe action potential more than one. One is bigger, one is small. That comes from different fibers. So there are biophysics calculations you can calculate. So for the larger fibers here, this is a muscle spindle we didn't talk about. This is one, the proper reception is the one where you feel something. So if I grab this, I feel I got a cup of a beer or get a laser point. That kind of feels come from this. Okay. And they are larger fibers. They travel fast. This is faster than frog nerve, sciatic nerve. And then for touch, this fiber, this about the speed that you would have measured in the frog sciatic nerve. Then there are pain temperature fibers. They are smaller. They are much slower. Remember, look at this one for pain. The travel is only about 1/10 of speed. So if you were to do following experiment, don't try it, but I tell you, if you fill the bathtub with water, but you don't know the temperature, you accidentally turns really hot. Or you turn it warm, but it suddenly becomes very hot. When water is filled, you're going to take a bath there. You take your foot, you stick there. Do you feel pain first, or feel you touch water first? Think about this. This is a real question. There's a hot water there. You don't know. You stick your foot, you step into that. What do you feel? You step on the water, or you feel, ooh, water is really hot, burning. Which one? Yeah?
You feel the water touching first?
Yeah. Because of the speed. Right. Because that question can be answered because of the speed. Even though your sensory, your pain receptor and the mechanical touch receptor active at the same time the moment your foot feels the hot water, both of them physically being activated. Because C fiber for carrying pain sensation are much thinner and travel much slower. By the time your brain knows the pain, it's too late. You already get burned. That's why I say don't try this. You'll get burned. So that's just one example for you to remember. What does it actually mean? That means that those two sensations are guided by different timing of this one. Anyway, so the point I want to make here is that both the type of a receptor as well as the fibers that connect the receptor matters for the sensory system. So this is a highly heterogeneous system compared with the visual system and the auditory system. And some of the larger fibers are myelinated, some smaller are unmyelinated. Of course, the myelinated fibers travel conduction velocities fast. And this data show you, if you look at different fibers here, A alpha, A beta, A gamma, A delta, and there are different diameters and a different conduction velocity. The thicker ones goes faster than the thinner ones. Okay. Now here I give you a summary of total of basically 16 type of efferent. Yes?
Is there an evolutionary purpose behind having the touch or proprietary receptors faster than
you could argue that it's more important for you to know what do you feel, so that I can react first than the pain and each other things. And that's probably a reasonable argument. Now, because most things you touch are not painful. Okay, that's probably most things we touch are not painful. Pain and each are in the minority of things we interact. Everything we interact every moment. You and I now, every body part is a part of touch. That's why part of touch evolved to have larger fibers and become more sensitive. Okay, the pain and the temperature system is not very sensitive in terms of time. Yeah, that's a good question. And now there are a total of 16 types of efferents. We touch a few of them. And this list of them. The efferents is the one that we don't have time to talk about. It's the running from the brain into the skin. There's a whole set of efferent fibers. Okay, so in artery system, again, we talk about one type of fibers going to brain through inner hair cell, and one type of efferent fiber from brain to outside through outer hair cell. That is the simplest structure compared with this. This is the most complex structure. Okay, so now you know if you want to design a robot, right? These days you read all the time when people lose their arm, you have a mechanical robot. There's in the movies all over place. For that robotic arm to function as a human arm, how many things you need to bring? You have to use the shape, force, temperature, all of that, right? So that's the complexity of this. And now the robot has it. Of course, you can